I'll talk a little bit about my research, which I've been doing both in my grad school and now since I came here for the last few years, largely talking about the development of luminescent solar concentrators. So before I get into that, we need to figure out how we collect solar energy. And generally, if you ask a person how do you get the solar energy, you get the photovoltaic cells, because most of the time that's what people see if you go, outside and you see photovoltaic cells on the roofs, and they say, well, we collect solar energy using photovoltaic cells, and you're not wrong. Vast majority of energy we have is collected using photovoltaic cells. There are issues with photovoltaic cells, starting from limits to efficiency. Part of it is built into the design of the silicon photovoltaic cells we use. Part of it is due to inherent maximum limit you can actually collect. You do need direct sunlight. There is a reason why they constantly insist that you want to be on the south-facing side of your roof, and you gotta angle them exactly right because you want to collect the direct sunlight as much as possible. And if for some reason you wanted to actually get through the photovoltaic cell, you would not be able to. They're not transparent, which is partly a good thing because that means that they collect all the sunlight. It also could be a bad thing if you wanted to have it transparent. So one of the other ways to deal with this is that you can concentrate the sunlight on the photovoltaic cells. And most of the time when you talk about concentrating things, you talk about geometric concentrators. In this case, what geometric concentrator would be is a series of mirrors or lenses which would focus a lot of sunlight on a small photovoltaic cell. And in this particular case, you can have very fancy arrangements from paraboloids to hyperboloids, and they're all very nice at collecting sunlight, but they also have several severe limits. So first of all, they require tracking. If you thought these require tracking, well, not really. Once again, you can put them on the south-facing wall and you can say, well, you get 80% efficiency and that's good enough. If you have geometric concentrator and you don't face it exactly towards the sun, your efficiency is going to be close to zero because they need to point directly to the sun. And the other problem, it turns out, if you concentrate about 2,000–3,000 suns into a photovoltaic cell, it's going to heat up. In fact, it's going to heat up a lot. And most of photovoltaic cells don't like when they heat up to, hundreds and thousands of degrees Celsius. So one of the other alternatives is something called luminescent solar concentrator, and that's what I'm going to be talking largely in this particular presentation. They're quite good at absorbing both direct and scattered light. They require no tracking because of that. They can be made partially transparent, which will allow you to use them as windows or blinds or something like that. And they have no dissipation problems, partly because they don't concentrate quite as well as these. We'll sweep that under the rug for now. So what is a luminescent solar concentrator? Well, generally there will be a transparent matrix of polymer or glass, and you'll have some sort of luminescent species doping these sheets. The incident solar flux is absorbed by these luminescent species. They then glow, they emit light, and then light is collected at the edges using photovoltaic cells. So the idea is actually not new. As you can see, the original publication here is in the mid-70s, but turns out that the luminescent species they used back then were dyes, and dyes are notoriously bad for long-term stability. If you ever had a bright shirt and you walked out in the sun for a bit too long, you'll find that the shirt is no longer quite as bright because dyes tend to photo bleach. However, in the past decades, new materials came out, things like perovskite materials, quantum dots, and other more stable dyes. So there is renewed interest in these particular kind of arrangement. So here, what we have is a video. Hopefully it will work. Oops, or maybe it won't. Aha! It's alive. It was alive for a short period of time. There we go. So what we'll have is we'll have the absorption of, should stop pressing buttons, of light, and then we have re-emission event, and the light is then collected. It's trapped by total internal reflection and collected by the edges. You can have other events, emission and absorption by different quantum dot or whatever your dye is, and then some of them will make it to the edge, some will get absorbed and never emit light. So that's kind of something we need to take a look at as to which exact things we want to use and how we want to use them to maximize the efficiency of these devices. So in the past, as you can see, we're now moving closer to current time, 2014. Minorities group actually managed to synthesize something like this, which is actually viable. So they used quantum dots with visible quantum dots, and they created 20 centimeter inside sheet. Well, it's actually not necessarily sheet, but they actually had a positive concentrating factor, which is great because up until 2014, all the prototypes created would not have a concentrating factor more than 1. That means that technically they were not actually concentrating the sunlight. So when the way the concentrating factor is actually calculated is how much light would you get from the edges of the cell versus simply putting your photovoltaic cell from the edge and facing it towards the sun. So if it's less than 1, that means that you're better off simply using your tiny photovoltaic cell from the edge and pointing towards the sun versus using this gigantic thing. But they actually made something that works. So they had a couple of ways, couple of very novel ideas here. They designed quantum dots themselves. So this is not something you can buy online. They actually created quantum dots with giant shells, which is great because they have no self-absorption. That is, if one quantum dot emits light, no other quantum dot will be able to absorb that light. So that limits those losses when one quantum dot emits light, the other one absorbs light, and then emits it again, or not emitting it again. And it also reduces the losses due to the escape cone losses of the total internal reflection. So they also prevented quantum dots from degradation, which also happens in quantum dots, by putting them inside the polymer. So instead of having ligands which protect the quantum dot from oxidation, they actually put polymers instead of ligands and then put that in the polymer sheet, creating a very stable environment. So this was obviously not meant as, commercial device, but it showed that these devices are viable if you work on them. So before I came to BC, there were a lot of other developments. We have shown that near-infrared quantum dots are actually really good, and they're actually a lot better than the visible quantum dots, which Minority Group used. However, we found that all quantum dots degrade very fast if you pack them close together. And as you have seen from the previous picture, they managed to get away with, get rid of that problem by making this very, very, very low concentration. So in their case, they don't have any closed packed quantum dots. However, if you do want to have a device which actually absorbs a lot of sunlight, you will need to close pack them, and then this issue is going to arise. Commercially available near-infrared quantum dots have other issues to talk about, and they are expensive. So that concentrator which I have shown you earlier, they had very small number of quantum dots, so they kind of got rid of that problem. They also had, if you have low concentration, you need a larger device to absorb more sunlight, which is not very practical. And the other thing which is kind of getting sidelines most of the time is, every time you see these devices being shown, they say, we have done the stability study, they did not degrade over 3 months. And you're like, well, problem is that you want them stable for years. So you really want to have a very definitive stability study for their performance for at least a year, preferably longer than a year, and which is not exactly something which you can ask, to do in a large research university, because they have other better things to do with their time than stare at the multimeter and see how much energy your concentrator generates. So there's also a question whether the rectangular geometry is the best. It's certainly the easiest, both to manufacture and to integrate. So for example, if you want a window, you probably want a rectangular window, which is, easy to work with. However, you can make cylindrical shells, and due to the interaction between these cylinders, you can have light trapped with them, and you can actually have higher performance than flat surfaces. So there's some question as to whether something other than a sheet should be used. And granted, if it's not sheet, it's not usable as a window, but you can probably stack a bunch of them and use them as the blinds. All right, so what have we been doing at BC? Well, first thing we decided that we need to make polymers if we want to put things into polymers. And it turns out that making polymer is a lot harder than one would think. That's one of our first attempts. More bubbles than polymer. But, as time passed, we kind of said, hey, we can make pieces of plastic which don't have a lot of bubbles and other bad things happening to them. So this is actually a lot harder than one would think. We also figured out how to make our own quantum dots. And the great thing here is that if you synthesize these on site, they're about 2 orders of magnitude cheaper than buying them online, which is a very, very big stimulus to actually synthesize them in lab because, well, we don't have that much money here. So we, however, did run into an issue with trying to put quantum dots in a polymer, because generally when you synthesize quantum dots, the solvent is toluene, and if you try to put toluene in a plastic, it dissolves plastic. So the idea is that we need to figure out how to either do the ligand exchange, similar to what Minardi's group did, or we want to dry the toluene out or ligand swap them. So figure out a way how to go from quantum dots and toluene to quantum dots and plastic without destroying quantum dots in process, which is what happened the last few times we tried it. So, however, quantum dots notwithstanding, we did manage to create some very nice sheets of material which, with rhodamine V dye and PMI, I apologize for just abbreviating this PMI, it's something very terrifying our one of the chemists gave us with regards to chemical name. So we have things, and as you can see, the edges are very nicely glowing. We have not really done much more with these until we got, and unfortunately the students who worked on that graduated, so I needed to figure out a new team, and so which would be able to pick things up. Last year we got new team, and we created new mold for rectangular samples. We streamlined quantum dot manufacturing. We started encapsulating quantum dots in PMA, and then COVID happened. So, of course, the COVID happened, right, closer to the mid-end of last semester, which is when most work is getting done. So some of the students from the group graduated. Other students are no longer capable of working on the project. So it's kind of put a fairly large damper on where we are. Hopefully we'll be able to restart this and get some progress. Hopefully not all progress has been lost. So if you do decide to come and figure out what you want to do, I mean, before I haven't even spoken about chemistry, because I'm not a chemist, and in fact I know very little chemistry. So if you do decide to work on quantum dot synthesis, you probably will need to have some background in chemistry, or you'd be willing to learn it and work with chemistry professors while doing so. What I can help is I can help you learn some physics which is necessary for this project. Now, depending on how far you want to go, this can just talk about the very basics, total internal reflection you cover in, physics 2, or we can talk about some condensed matter or some other fun things which go into why quantum dots do what they do and how they do things. You can work on design. You can figure out whether rectangular geometries are best, or what other geometries we can try. You can work on manufacturing. We can create these things, hopefully without making too many bubbles in the process. You can characterize these things, figure out how well they work, and do stability studies and things like that. So there's a lot of things that you can do. And if you're on the computational side and you want to work with, this project, you can certainly model a lot of these things and figure out which of these things would work better, so you don't need to, actually jump in and start manufacturing things. There are also a large number of other projects which students have came to me with, which I'm very happy to support. So if you have a project you have in mind, which involves, a lot of dirty, let's do crazy things like rotate dry erase markers to see if we can get them to work in the centrifuge, well, I'm certainly, we can certainly do something like that. Plus, there are some other interesting projects which I have in mind which students might be able to contribute to. So, that's it. If anyone has any questions, please ask.